tell you what I'm looking at for problems here for the Unit 6 part of the exam. When you do the exam, it's going to be out of 100 points like normal, or maybe a few extra. All of the points for the Unit 6 problem are going to feel much smaller than normal because it's only 50 points or about half of the exam. But don't really pay attention to the points. Don't, you know, it's all going to be scaled down. But just do it like you would normally do it. You know, the 15-point problems might be closer now to 7 or 8 points, but it's just all because that's only half of the final. Yeah.
Are you gonna get like any extra problems on our natural and physics for us to do, or just, you know, we just have to go back and look through it?
I might for this. You have, I think, a good selection of problems on the current, the last homework for heat and everything. If I find some good ones for extra practice, I might put some more up over the weekend, or give you a handout that we can work on Tuesday in class or something with some extra ones. I don't have a whole set already that I've chosen, but I might. So kind of just.
It would be really nice if you could.
You want to do some more?
Extra
You
problems
want more
in there.
work?
Yeah.
If you want more work, I can
Some
make
of
more
these
work.
problems are kind of hard.
Okay, I'll see if I can find some. I'll come up there. If not, this weekend, definitely get some more by Tuesday probably if you want a few extra practice ones. On the part 1 side of the Unit 6, Young's modulus, using that equation with the force per area, is equal to Young's modulus times the delta L over L naught. There will be a question on that if you've done those in the homework. Those are usually pretty straightforward. You just need to know the equation, look up the constants, and don't forget your area equation, but at least I'm giving you that one over there for the circle. And some places where people are getting mixed up is that they're not always solving for the right thing. The delta L is the amount of change, the L is the final length, the L naught's the initial. Know what that is. That's going to be, you know, probably I would consider a pretty short problem, not very long, but there will be one with that. I'm relating gauge pressures to atmospheric pressures, absolute pressures. That can be mixed in with something else, as you've seen in other problems. Determine the pressure in a fluid at some depth. That, you will have to use that equation somewhere. That's this one here. P is equal to P naught plus rho GH. Some people have been getting mixed up when you're mixing that in with ideal gas problems. Because with the ideal gas law, you've been a lot of times using P1, V1 over T1. It's P2, V2 over T2. And sometimes you're mixing up the P and the P naught with the 1 and the 2. I also see people mixing up this P naught right here, thinking that is the initial. Especially when you're combining these with the ideal gas equation. This is always the pressure above the point right here. Yeah?
Are you gonna give us the constant for P naught, or?
That I'll give you. You need to know when to use it. I'm not going to call it P naught. I might just call it atmospheric pressure because it's not always going to be your P naught. But I will give you that number of the 1.01 times 10 to the 5th. But it isn't always P naught. Okay? It only is if you're at the surface of an open container. Okay? You'll use this equation. We've seen a couple times now how you can combine this. And we've had to use that with ideal gas problems a couple times in the homework with the scuba diver, in class with a glass of beer or something with the air bubble rising. So we've seen that a couple times there. Pascal's principle we're not using. Buoyancy and Archimedes' principle we'll definitely have. That might be one of, normally that might have been one of the 15-point problems. It'll be lower on the point scale here, but those usually have a little bit more work. The ideal gas problems aren't very long. There's not a ton of math there. It could be longer if we're combining this in the same kind of situation there, but those aren't too long. The buoyancy, though, is usually a little bit longer of a problem than these ones can be. And I think you've already seen how those work out, how that might end up being worth a little bit more. Your temperature conversions, I'm giving you those equations. You just need to make sure you know when to use them and when to convert. Remember, this here is a very easy place to forget kelvins because your units will cancel out if you put them in here. But you can't use Kelvin temperature. You can't use anything other than Kelvin temperatures in this equation right here. Thermal expansion with the delta L's or the delta V's. You know, the delta L is equal to L naught alpha delta T, or the same thing with the delta V is equal to V naught beta delta T. You probably won't have both. I mean, it'll just be one or the other. They both basically work the same way. You'll have a thermal expansion problem. Those tend to be shorter problems also. I don't usually mix this in with an ideal gas problem or anything else. It's usually kind of a standalone problem where if you know the equation, you can look up your constants. I think you have some questions like this topic here, like the ideal gas law, this here, that they're pretty self-confined, that they're just expansion or this kind of expansion here. If you know the equation, they're a lot easier than some other problems. They're a lot easier than calorimetry, they're a lot easier than buoyancy, I think, and so those on our lower scale now, with only being half of the final, those are probably just 4 or 5 point problems, not very much for those. Number 8 we crossed off. Ideal gas law I already talked about, that's all that first slide right there. Buoyancy I didn't write down any equations here for. There's obviously more we could talk about with that, but there will definitely be a buoyancy problem on there, and that I would expect to be more points than each of these individually. That might be a 10-point problem or something. That's equal to the weight of the fluid displaced, just kind of by definition of Archimedes' principle, but that's related to the density of the fluid, gravity, and the volume of the fluid displaced. But that wasn't enough. What else did we need when we were doing buoyancy problems? What did we always do for buoyancy problems? Yeah, this is a force. You won't get your answer from this by itself. There's going to be more to it. And those usually came from you drawing a free body diagram. And maybe some of the simple cases you didn't draw a free body diagram and you just said the buoyant force is equal to mg. Well, that's only in the case when there are no other forces. But the minute there's a scale on there, there's other forces, that's not going to work. Just draw your free body diagram for any case, set up your equation, and for the buoyant force, you put that in there. And you've seen that some of those can be a little tricky, a little difficult with knowing which densities and which volumes to use. Sometimes it's the volume of the fluid is the same as the volume of the object, but that's only when it's completely submerged. You've done homework on that. If you want to review topics like any of the things that we're talking about here from Unit 6, then next week just come in with some questions or send me an email if you have something specific you might want to look at on Tuesday. We already been through all the second page here today. We talked about that with the kinds of problems. I think the bigger point value problems on the Unit 6 material would be buoyancy, calorimetry with all the cues. I mean, those are the ones that have been a little bit longer as far as some of the math has gone with what we've seen. And you saw definitely how that worked out with longer math on that problem from lab last time. And some of the buoyancy ones are a little bit more lengthy than I think these ones over here. You have a few easy points of definitions and phase diagrams and defining the kilocalorie on here, so make sure you study those and remember those. Those are points you don't want to miss because you already know the question. Okay, going back to everything else. The first half of the points, or whichever first or second half you call it, about half of the points on this final exam will be over units 1 through 5. It is, as I've been saying the last couple weeks now, it's basically all conceptual questions, very little math. You don't need to know all the equations. Mostly in the form of multiple choice. I have, right now, 23 questions and a free body diagram. So, and a free body diagram. If these are 2 points each, that's 46. If this is 5, that's 51 points here. About 50 points with what I have it right now. I might change a little bit. I might add 1 or 2. We may get over 100 at the end, but it's going to be about that number of problems. Right now, 21 out of these 23 are multiple choice. 2 are just, I ask you a question and just tell you to explain, but the explanation usually is just a sentence and nothing very long. Okay? It's a very short, brief explanation. But I do have 2 where I just want you to not guess an answer. I want you to write something that shows me some kind of understanding. But those won't be very long. Okay? So that's about what it is right now. To study for this, start anywhere really. I don't care about the order here. There's a few places that you can go back to study. I would look at your old exams, look at all of the conceptual questions that are on there. Those are the kind that I've been giving you all semester long, where some have been multiple choice, some have been short answer, but I think you've seen that format from me on exams. You've also seen it on your Mastering Physics homework. You had a fair amount of practice answering conceptual questions, multiple choice format questions, and brief explanation ones on the Mastering homework throughout the semester. You can go back into any of your old assignments and click the rework for practice and go through them again if you want to. That's going to take you some time to go through all the assignments, but it could be good practice there to go through that. Another place would be in your book, and I have pulled questions from old exams or homework questions or from the book here. Okay, so there's so many questions you can't study them all and recognize them all when you get to the exam, but I mean, I have kind of gone straight to some of these places where I'm telling you right now to look for questions to put on there. So if you have your books, and if you don't, it's fine, just make a note of this. Open up to page 58 if you have your books. This is a very good source of questions to study from, because at the end of every chapter, you have a selection of, in this case, 20 multiple choice questions over chapter 2. I have definitely pulled questions from some of these here, I've flipped through here, and the book can do for you. It's pretty nice.
Sure, it is long.
Or maybe I should have told you a long time ago, I apologize for that. But this would be a very, very good place to start studying. I think this might be kind of more compact than going through and clicking on all your assignments and kind of trying to find where they're at. We did have one assignment that was all multiple choice, so that might be a good kind of one where at least you'll know where the questions are, that the whole assignment was multiple choice. But, yeah, I mean, they're all good multiple choice questions here about the concepts usually. Sometimes you might have to do a small calculation to figure something out, but they're most times going to involve things where you don't need the equations. So, you know, like if you look at these, back from Unit 1, we'll start talking about this now. I'm going to go over this, we'll talk about this for the rest of the class today. And what I'll do now and what I'll do next week on Tuesdays, pretty much just kind of run through some of the objectives, remind you of some of the topics and the things that we need to remember, and then just kind of read through some of these questions that just pop out at me when I'm looking at them. And when they pop out at me, they may be the same ones that pop out on your exam because I liked them before, and I might actually kind of see one there that I read again. Some of these may be ones that you see on the exam, but they may not. There are plenty of good ones here. I had plenty to choose from. If you look at number 1 right away, it says a scalar quantity has magnitude, direction, or both magnitude and direction. These are all things that you need to remind yourselves of. What are vectors? How to find the sum of some vectors? How to find components? What is the vector nature of all the quantities we've been measuring? Velocity, acceleration, all those kinds of things. Remember, a scalar was just magnitude. Velocity had both. There's questions on here. Number 6. On a position versus time plot for an object that has a constant acceleration, what would the graph look like? That's another question that I could ask you. Remember how we made those graphs for
Vertical line.
position versus time, velocity versus time, all those things. If you can go through all these questions, you'll get a lot of good practice. Answers are in the back of the book for the odd questions. The even ones, I think you should all be able to figure out if you've been in class, but if you're not sure, you're not confident in your answer, go back and reread your notes and try to figure it out, or check with me on Tuesday or send me an email. I don't have an answer key that I'm just going to put out for all the questions, but I think a lot of them you can probably figure out with just a little bit of effort in your notes. And, you know, number 6 there, if you have an object with a constant acceleration, we want a position versus time graph. Well, let's first start with what would the acceleration versus time graph look like if we had constant acceleration? Now, let's assume it's positive acceleration. What would the acceleration graph look like if it's a constant acceleration?
Straight.
Is time changing?
It's constant.
Time's constant too.
Oh.
Time's not constant. With time, the acceleration is constant. So time can change all at once. It's just clock's always ticking.
But then just horizontal.
A horizontal line. Not a straight line going up like this, but a straight horizontal line, because the acceleration does not change. Okay? But we want a graph of position versus time for something that's accelerating. Now, how do we relate all these graphs to each other. How do I get from position versus time to velocity versus time? What
The
was
slope
the
of-
slope? The slopes of your graph get you to the next thing. So the slope of position gets you to velocity, the slope of velocity gets you to acceleration. Because velocity is the rate of change of your position. Acceleration is the rate of change of your velocity. Right? These are all things that we learned before, but you probably haven't thought about in a while. I think with a little bit of review, you're not learning anything new, but go back and remind yourself of these kinds of things. That's a very good place to look in the book here for some questions to practice those. Here, we should expect, well, if my graph was like this, what can I say about my velocity?
It's constant.
Because the slope is constant. My slope, so if this would give me constant velocity, which would mean my acceleration is equal to what? 0. If you want a changing velocity, because a change in velocity is what gives you an acceleration, then what kind of graph should you have? A curve. And you got an option there, I'm sure, for something that's curved, horizontal. Yeah, so D there for that question there. But all these properties about motion, velocity, acceleration, remember the velocity vector points with your motion, the acceleration is related to the velocity direction. How? How is the acceleration related to the velocity?
Acceleration is positive if it's going towards direction, or going the same as the direction.
Careful with the plus and minus signs, because we've seen with things like this, when I throw this up in the air, what's my acceleration on the way up?
Positive. No, it's negative.
It's always negative 9 pointing. Because when I go up, it's slowing me down. And remember, we didn't learn about Newton's second law this early in the class, but now that we know when this is in the air, what force is acting on it?
Gravity.
Which way is it always pointing?
Yeah.
Always pointing down. If there's a net force, there's an acceleration in that same direction. Gravity's always pointing down, net force always points down, the acceleration's always straight down. The minus sign depends on our coordinate system and which way we're moving. So I can't always say that a negative acceleration means that we're slowing down. If I'm speeding up that way, which way is my acceleration? That way. So it would be positive if that's my coordinate system. If I'm speeding up that way, which direction is my acceleration? That way. So it could be plus there, minus there for speeding up in both cases. When I'm going up, I'm slowing down when I threw this up in the air. But my acceleration is negative. So when you're slowing down, negative might feel good to make you think that you're slowing down. But remember, when I'm going back down, we are speeding up in the negative direction, so that would be a negative acceleration. So with velocity and acceleration, you go with the velocity if you're speeding up, against it if you're slowing down. Plus or minus signs really depend on a coordinate system and the motion that you have. Okay. What about if you're moving in a circle?
It's constant changes.
Accelerating.
It's not accelerating?
It's constant.
In which direction?
Solar system.
Always toward the center if you're moving the circle. With uniform speed. If it's not uniform speed, remember we saw it when we got up to rotational motion that we could have both a tangential and a centripetal. And we have a possibility of having both of those. But for uniform speed, it goes just toward the center. Is this painful? Taking your minds back to these things here. I think with a little bit of review, you have until, you got a whole week, right? We're taking our test on Thursday, so you have some time. I think you can kind of get through your homework, get all that Unit 6 stuff down. We'll spend more time talking about this on Tuesday. We still have more time now. I'm going to keep doing this now. For any of you who have other more important things to do, which I can't imagine you having in this class, if you feel like you're comfortable with all the stuff that I'm talking about now and you don't need to go through all that on Tuesday, I'm not going to give you an in-class assignment. If you had another test that day and you wanted to prioritize and wait to study this until after, I'm not going to take any points off or think any less of you if you're not here on Tuesday. We're going to do more of the same of this right here, and I'll take questions. It's not going to be very formal in the sense I'm just going to kind of go through problems like I normally might, but there won't be any points for it, so our test is on Thursday in this room. If you're not here Tuesday, I'll be okay with that.
If we are here Tuesday, but we do have another test that day and we leave early, you won't? be
That's fine
offended?
also.
Okay.
Yeah, I mean, I won't be offended there either,
Would you
especially
like-
if you're wearing purple and gold.
might be.
But yeah, that's fine too, like if you just wanted to come for a
Are you
little
gonna
while.
go through the whole lab time? I mean, is that? are you
Probably
using-
not.
Okay.
Now, James wants me to.
Well, you like the time, man, when it
and
says
I'll-
10:20, we're
I'll
out at
be there.
10:21.
Yeah, I mean, I'll be available that whole time.
Okay.
So if we wanna go and carry over into lab or stay in here and do some more, that's fine. If we wanna kinda go over more from unit 6, I'll be available. Chances are, we won't need to. There are a lot more topics and questions of these right here that will probably feel like they're coming from the first 3 or 4 units. There aren't that many questions on sound and waves, because there just aren't that many there. There probably aren't as many on rotational motion as there is on the whole first 3. Because the first 3 were those big ideas about motion, energy, velocities, momentum, all those topics. We did it all over again with rotational motion, but it'll probably feel like it is more heavily weighted toward the first 3 units, because there's just so much there about motion, forces, and energy, and kinematics. Okay?
So, you said that units 1 through 5, that's the only units we're testing over?
For this part of the exam, unit 6 is on there like normal.
Alright.
And I may have conceptual questions on unit 6 in the same form of multiple choice. But with that part of the final, I've got about 50 points worth of material from units 1 through 5. Yeah, I mean, definitely go through these questions that are here. I've seen some of these. Some of these are on the final. A negative acceleration can cause an increase in speed, a decrease in speed, or either A or B there. We just talked about that. It can be either one. It really depends on which way things are moving. All the stuff on free fall, there's a whole section here on free fall. We talked about that a little bit already, but when we throw that object up in the air and it's in free fall, then you should be able to tell me all about that motion. You should be able to tell me about what the acceleration is, what the velocity is, and not numbers necessarily, but just understand that motion. When it reaches the top, so we said already, I'm going up, my acceleration was negative 9.8, we're slowing down, I reach the top, what can you tell me at the top?
Acceleration is 0.
Acceleration is not 0.
Velocity is zero.
Velocity is 0. What's the acceleration? Why is it 9.8?
Because gravity is still.
There's still a force of gravity acting on it, even though it's not moving at that instant. That force is still there, there's still an acceleration. That acceleration is going into changing the direction of it at the top, okay? Not to speed it up or slow it down, the same way that it was kind of moving up or going back down. Okay? You've got a handful of questions there about that. On free fall motion, I'll let you research some more of those on
Are
your
we gonna
own.
have any on projectile motion?
You will definitely have some on projectile motion.
Are they just gonna be like conceptual questions or like actually looking at?
What's the answer to that question?
Conceptual.
There are no working out problems from this part
So
here.
none at all?
Unless you want some, I can make one for
Yeah,
you. But yeah, there won't, you don't need to, you need to remember that you have to separate the motion into X and Y components and think about how we broke those up into the two different components of motion. But all those kinematics equations, you won't need to calculate things. Let me go back to vectors a little bit and kind of just look at the first page of the objectives. Units, I'm not gonna ask you for the SI units and, length, mass, and time like they're on here. You're using that all throughout Unit 6 also. I mean, you've been using units the whole semester, using your powers of 10, unit conversions. Those aren't questions that are on this part right here, because you're still using it all throughout Unit 6. The parts about vectors, defining a vector, know the difference between a vector and a scalar, resolving a vector into its components, combining components to find the magnitude and direction, doing vector addition, all those things you need to know how to do, but you're not going to do all the numbers for it. But you need to understand those concepts of if you have some vectors, and I gave you a diagram with vectors, you should understand how to interpret that diagram. You should be able to look at a diagram and tell me something about the vector, or be able to draw a vector diagram. Okay? Finding the component of a vector may be something you can do. That might be a little bit of math that you could do if it helps you solve a problem, but there won't be a whole lot of that. But you should still know how to find the components of vectors, and of course know what they are. On the next page, constructing a graph of data. We've been doing that as kind of a lab objective all semester long. That's not a question on this part here. All the questions about graphical analysis, you might have some things with graphs. So those are kind of mixed in with different velocity or acceleration graphs on the objectives here. But have an understanding of the difference between speed and velocity, distance and displacement, position, velocity, acceleration, and time. That's what all these objectives are here. Don't go through these kind of looking for a question on each topic here, but just kind of go through these in your studying maybe and just remind yourself of what all these things are. And if you start asking yourself, well, anything about solving a problem with these, just, you should know what the answer to that question is, that you're not solving problems here. You might need to think about some of the processes that you've used to solve problems to understand the questions, but there's really not much at all where you need to pull out equations and do any math for these here. You will have equations for the free body diagram though. It's going to be in that same format that I've given you before. There's one of these now, there might be two. I have one there now, I don't know if I'll add another one or not. Okay. But you guys know how to do those. Yeah. Number 15 on here was, and a couple on here were about the graphs. 12 and 15 were about the graphs. Remember that your slopes tell you something about the velocity of the acceleration. All of the kinematics equations, like 16 through 18 there, we're not going to be using those. But with projectile motion, which was one of the ones on there, you need to remember what a projectile is. You need to remember the properties of motion that we have here. This can land back on the ground, or it can land maybe up here at some vertical level up there. What are some things you can tell me about projectile motion? What do we know about things, let's say up here? What do we know up there? Which acceleration is 0? See, when we switch to these, we had to start switching out and be thinking about the x and the y motions separately.
The Y.
The y acceleration is always what?
9.8.
Yeah, ay is equal to your negative 9.8 meters per second squared, or negative g. I'll use the g and the 9.8 and interchange them sometimes, and you see those. Those are the same thing. So what else can we say up here at this point?
Your velocity in the y direction, 0?
Good. It's only the y velocity that's 0. What can we say about the x velocity?
It's constant.
Good. Vx is equal to the initial x, which is constant throughout projectile motion, as long as what?
There's no friction.
No
Or no-
friction, air resistance, no forces in the x direction. Because what determines the acceleration is the net force. When it's in the air, moving across the room or whatever, the only force acting on it is the gravitational force. Okay? And other forces could be there, but if we're just throwing something in the air and it's in motion under the influence of only that right there, then we have always said that our AX is equal to 0. And that's not going to change. I'm not going to give you problems where we add on some other force there, but for our projectile motion, we've always treated it with that case. So the x velocity is constant all throughout the motion. The y is changing just like it would have been going up and down based on the acceleration due to gravity there. Okay. I can say things like Vx is the same everywhere. I can say that the Vy's are the same only at the same level. Right? If I start here at some Vy, then I'm going to end down here at the same. But that was only when they started and ended at the same level. If they go to a different height, then we don't know that, and we can't say that. But all the equations you just don't need. Now, if you think you need the equation because you want to solve something, or maybe you think solving something or understanding the equation might help you answer a question, then if you ask me for the equation, I'll probably give it to you. But I don't give you a list of all the equations from the entire semester because it's just too much to look at that you probably don't need. But if you remember that an equation exists, and you think you might need it, and you ask me for it, there was an equation for velocity or something that you think might be helpful. If you ask me for what it is, I usually will give it to you, and I'll probably put it up on the board just so that everybody can see it if they want to, but you really won't need much. Don't resort back to trying to solve equations when you're answering these questions. And then I think you'll see that. I think you'll read through the questions in the book if you do that, and you'll know what I'm talking about, what the format, the style of questions you're going to have here. Okay? But there's definitely conceptual questions I could ask you about with that, and we've seen those before on that first unit test. You have questions about all these things in unit 1 exam. So that's like chapter 2 there. Chapter 3 is gonna have some more questions on here about projectile motion. For your chapter 3 questions, and that's on, starting on page 94. You're gonna see certain sections in here that just won't be relevant to, you know, what we did. And when we got to unit 3, we had already had our discussion about vectors, and we did that in class. There's a couple of sections here, like 3.1 and 3.2 there, that are about vector addition and some other things. If you start reading questions that feel really completely foreign, and you've been in class all semester, then they probably are ones that, you know, you wouldn't expect to see on the exam. The 3.3 section though about projectile motion, that's definitely a good 3 or 4 questions there that would be relevant to this chapter. But the one with relative velocity we did not do in chapter 3, so you won't need to worry about those. That question about the football being thrown on a long pass, that was on our unit 1 exam. I don't remember which one it was, the horizontal or the vertical, but, you know, a football thrown on a long pass is thrown on a long pass. And we want to compare the ball's initial horizontal velocity component to the velocity at the highest point. Well, we already said the horizontal velocity is constant. And then they ask you the same question there about the vertical component of velocity at the highest point. Right? Those are the kind of things you should know about, some of the kinds of things that you might be asked about projectile motion. Okay. The next unit was about force. There were plenty of questions about force and Newton's second law, Newton's third law, all Newton's laws. There's a lot of good questions here. Number 4 on page 131, just looking at it now, says, if the net force on an object is 0, the object could be at rest, be in motion at constant velocity, have 0 acceleration, or all of the preceding. Because if it has a net force of 0, there is definitely no acceleration. Right? And so it could be at rest. It doesn't have to be at rest, it could also be moving at constant velocity. Those are all 3 cases there where you would have 0 net force. And there's plenty more here in that section. 3 or 4 questions there on Newton's third law about those action and reaction forces. Questions about friction. We'll go over some more things with those next week also. And then our free body diagram is going to come from that unit. And as I said, on Tuesday, this really won't take us that long. I mean, I could read through every question here, and we could go through them together if we wanted to. And so we'll just kind of do however much we feel like doing, and I'll take questions. But, you know, it could take us however long it wants to take us to go through the rest of the force unit and questions on there. As I did with the unit 1, I might kind of read through some of the objectives that are on here just to kind of remind us. But with the force unit, it was all about Newton's laws and forces and free body diagrams. Know about all of our different forces, you know, weight, mass, normal forces, the difference between weight and mass. These are all things that we will see on here. We'll start getting into circular motion and centripetal force and all of that here also. But that's what we're going to do on Tuesday. I think it's useful, but I also think that there are some people who have been pretty comfortable with material all semester long that, you know, it's just, I know you're all going to be here because you're always here, so I'm not expecting you not to be here, but if you really have something, a test that day or something, I'm going to do more of what we just did right now, so you at least know what we're doing then. If you chose that you wanted to miss that. The only thing you wouldn't get on Tuesday is me handing this back to you with this assignment, so you can come by my office and pick that up, but I think you could all do this again if I gave you this blank sheet of paper, so you probably could do that again, I would hope. Okay. So that's where we're headed on Tuesday. I heard there was a chance of some weather next week, but that shouldn't affect us here in this class. I've got office hours now, tomorrow.
Unless
you guys.
Nice job, Beaver. Weathermen are like, it's gonna snow and ice, or it's gonna do nothing. I'll be in tomorrow to get my paycheck. Seriously, how does that work? If I said it could be 5 or it could be 6, I'll still be there tomorrow.
But some meteorologists do a lot more than that.
I know, but the one that
But the
records.
ones that we see on TV might not always.
Like, how do you plan for that?
Just move to California and say it's sunny every day.
Yeah, no joke.
Sunny with a slight chance of rain.
Yeah.